Similar concave mirrors are capable of focusing solar radiation well in this way, and we can produce electricity if this place is the location of a small solar panel or a Stirling engine. Or we use this third option where a mirror dish focuses solar radiation onto a receiver, inside which the radiation is converted into thermal energy that produces steam for a turbine. Solar electricity from this turbine can be cheaper than the electricity from thermal and nuclear power plants and better than from solar panels because the turbine uses heat storages which provide opportunities to generate electricity at night, on non-sunny days, and in non-sunny winter just as well as in summer. And I will describe these heat storages in 5 minutes.
Now I remind you that a mirror dish must rotate from morning to evening according to the movement of the sun across the sky, but this video will show you a different method where a mirror dish is motionless and does not require such rotations from morning to evening. I did a lot of experimental testing of our new method with a variety of mirror types, which will be described in more detail in 6 minutes. Let you come up with the idea of our new method yourself, and the following experiment with this concave mirror will help you invent this method yourself. This mirror will be motionless from morning to evening. The west-east line is here, and the mirror creates this spot of solar radiation on the white screen. Now it is morning, and these are points in time during one day. You can see that the spot goes along this horizontal line from morning to evening. Therefore, you understand that our receiver must move approximately in such a way that the spot from our concave mirror is inside the receiver all day long. The following experiment will help you ensure that everything will work well, and this motionless mirror creates this spot on the white screen which moves in exactly the same way as our receiver should move during one day. We see that the spot is inside the white screen from morning to evening. Of course, you will object that the sun is low on the horizon in the winter months while the summer sun is high. That is why you come to understand that the mirror should be almost vertical around the winter solstice, but after that we have to change its vertical angle several times until this position, which is required around the summer solstice. After this, we change the position of the mirror several more times during the next 6 months. Now I am showing how I change the vertical angle of the mirrors on my solar station, but perhaps more southern geographical latitudes will require changes in this structure. Thus, these two features distinguish our mirror dishes from those more expensive devices which must rotate from morning to evening. In addition, we must distinguish our mirror dishes from this class of devices where the receivers are located separately from the mirrors and from this class where heavy mirrors are motionless all year round, and I plan to describe these two classes in my future videos. Let's use the idea of our motionless mirrors to invent a new solar power plant which will collect solar energy from an area of 100 square kilometers to produce as much electricity as a nuclear reactor. First of all, you understand that our power plant will consist of millions of concave mirrors which must form long rows. We also understand that every concave mirror must have a similar receiver, and now I am showing a variety of receivers for heating liquids with solar radiation from mirror dishes. This is one of my receivers, and you can notice that the height of the receiver is several times greater than its width. Of course, we must have a mechanism to move dozens of receivers, and perhaps this blogger's solutions will help us. He solved a similar problem of simultaneously moving his mirrors using this mechanism, a description of which can be found on his YouTube channel. We also have to choose a heat transfer fluid for our receivers, and therefore we can use many years of experience in solar power plants of this type. We know that these mirrors focus solar radiation onto this receiver, where the radiation is converted into thermal energy which heats thermal oil to a temperature higher than 300 degrees Celsius. So, this pipe is a path for the circulation of similar thermal oil with a temperature of about 300 degrees, which is constantly heated by our mirrors during sunny hours. But let's continue to take an example from solar power plants of this type, where solar radiation heats the thermal oil inside these receivers to temperatures higher than 300 degrees. This hot oil moves through these pipes to the center of the solar power plant, where a proportion of its thermal energy produces steam for the turbine. The rest of the oil energy heats thousands of tons of the substance in these heat storages to a temperature higher than 300 degrees, and then, in the evening or at night, this hot substance produces steam for the turbine. But one of my old videos describes the possibilities that the hot substance can produce electricity for several non-sunny days in a row if that substance is concrete, gravel, sand or other cheap materials. In addition, our solar power plants may have the ability to generate electricity during a non-sunny winter as good as during a sunny summer if the heat storage is a large mass of soil or cheap waste, as described in this old video. This is the formula for the cost of our solar electricity at 5 cents per kilowatt hour, and it is cheaper than electricity from thermal and nuclear power plants. This is accounting for our heat storages, this is accounting for turbines, and this is accounting for other equipment and its maintenance. But here we see that about half the cost of our electricity is determined by the cost of thermal energy from our solar heaters, which should generate heat at a cost of half a cent per kilowatt hour, and this is an example of achieving the goal. This formula leads us to the cost of our thermal energy at half a cent per kilowatt hour, and our receivers are taken into account here, and this is an accounting of structures located between the ground and the mirrors. But we have to pay attention to these numbers to understand that our mirrors and their maintenance will determine more than 30% of the cost of our solar heat, and therefore we should focus on finding the cheapest types of mirrors. I have often made mirrors from this very cheap reflective film at a cost of 25 cents per square meter. My old videos showed this concave mirror, which is made from that reflective film and this mesh. Also, my videos showed experiments with this type of mirror, where that reflective film is fixed on a sheet of cheap porous plastic, and then such mirrors can form a similar concave mirror. In addition, transparent and reflective films can form a balloon with one surface of a concave mirror, and my videos describe the experiments with this type of mirror. I am also trying to do experiments with the reflective film that is glued to a thin metal sheet, but you can find many other types of mirrors from cheap reflective films from other bloggers. The purpose of searching for a cheaper mirror is this criterion, which combines the similar lifespan of a cheap mirror and the cost of replacing it. My measurements of the lifespan of the cheap reflective film say it is about 1 year or a little more, but the lifespan may be reduced by hail or hurricane. But I remind you that I did these experiments with the cheapest film based on one layer of mylar 20 microns thick, and we can find more expensive reflective films with a lifespan of up to several decades. Such a long lifespan requires a different criterion, and here we see that the total cost of manufacturing and installing a mirror can reach $10 or $20 per square meter. It can be a mirror made of stainless steel, glass, anodized aluminum, reflective plastic or other material with a cost of about $10 per square meter and a lifespan of about 20 years. In addition, the weight of the mirrors should be light, otherwise these actions to change their vertical angle may require excessive physical effort. So, we can use many types of long-lasting mirrors, but only if their manufacturing and installation are automated. Unfortunately, 1 square meter of our motionless mirrors will produce almost 3 times less thermal energy than 1 square meter of these mirrors with very expensive devices for turning from morning to evening. This fact is taken into account here, and one of the causes of this fact was observed in that old experiment. We see that this solar radiation spot increases in the evening hours, and this phenomenon noticeably reduces the amount of solar radiation in our receiver, because the receiver area should be 30 or 50 times smaller than the mirror area. The morning hours have the same phenomenon, and therefore we understand that our heat generation will only be during 5 or 6 hours in the middle of the day, but this time interval can be increased thanks to the following method. I remind you that our mirrors should form such rows parallel to the west-east line, but if you make the rows like this, that time interval will increase by several hours. These are the points in time of one sunny day, and we see how the temperature of the thermal oil changes at the inlet and outlet of the rows of receivers. This is the direction of movement of the thermal oil in the morning, but the direction changes at noon. And I remind you that this method increases the time interval but almost does not change the amount of thermal energy per square meter of mirrors. Let's pay attention to this shadow of our receiver, these shadows from its mounts, and this shadow from its pipe. It is obvious that those shadows reduce the generation of thermal energy, and these losses can be up to 10%. But now I am showing how we got rid of those losses, because now the receiver is fixed slightly below the geometric center, and therefore those shadows are here, below the surface of the mirror. In addition, we can notice that now the mirror is more vertical compared to this first case, where the receiver was fixed opposite the center of the mirror. This is the same but for positions that should be in the summer, and it is important to note that this case of the receiver below the geometric center reduces the problems of these devices for changing the vertical angle of the mirrors. Now we will check whether everything will work if the receiver is located below the geometric center. We see that this spot is located inside the white screen, which imitates our receiver and moves from morning to evening.